Welcome to Dr. Boxy Teaches Electromagnetism. In the previous lesson, we introduced the concept of scalar and vector fields, and we started our study of differential calculus. We ended with the meaning of the del operator, that upside-down triangle we see in the equations next to me. Today we continue that. We will look at the concepts of divergence and curl, and we will study the differentiation rules for all of the special kinds of derivatives we introduced. So let us get started. We define the divergence by using a dot product between the del operator on the one hand and the vector field v. Now the del operator again is a vector whose x component is d dx, and remember that if we take the dot product between two vectors a dot b, we write it, one of the ways to write it at least, was ax bx plus ay by plus az bz. And we will do exactly that. We will multiply the x component of del, so d dx, with the x component of v, so vx. But again, it's not an actual multiplication, it's an application. So we're applying d dx on vx, so we get the partial derivative of the x component of v with respect to x, plus dvy dy plus dvz dz. This thing is called the divergence of the vector field v. What does it mean? Well, the actual interpretation of the divergence will be given in the next lesson when we will learn integral theorems on vector fields. But for now, let's try to understand the intuition behind it, and the actual statement of the theorem will come in the next lesson. Let's think, for instance, of a vector field that looks a little bit like this. So it's a vector field that points away from a certain point, and as you go further and further away from it, the size, the magnitude of the vectors increases. Now think of some closed surface. Imagine I'm considering some closed surface here of some shape, and I want to know how much vector field net is leaving that surface, that volume enclosed by that surface. Well, there are arrows, there is an amount of vector field going into that shape and an amount going out of it. If there is as much going in as going out, the divergence of that thing will turn out to be zero. If there is more going in, the divergence will be negative. If there is more going out, the divergence will be positive. So the divergence turns out to be related to the amount of vector field going away from a certain point, the amount that it diverges away from it, which is why it is called the divergence. If we look at another example, this vector field, it's a constant vector field. Any shape I would take, any closed shape I would take, there is as much vector field going in as there is coming out, so the divergence of that will be zero. And if we take this vector field, notice that as you go higher and higher, the magnitude of the vectors increases. So if I take some closed shape, the amount of vector field going out will be larger than the amount coming in, and so the divergence of this thing will also be positive. Let's try to actually calculate the divergence for these three examples. So for the first example, this vector field, it is given by the expression x times x hat plus y times y hat plus z times z hat. What is the divergence of that vector field? Well, it is the derivative with respect to x of the x component, which is just x itself, plus the derivative of the y component, which is y, with respect to y, plus the derivative of the z component, which is z, with respect to z. And each of these is 1, so we get 1 plus 1 plus 1, in other words, 3. So we indeed get some positive number. The second example was this vector field, and it can be written as a vector field whose x and y components are 0 and its z component is just 1. It's 1 times z hat. What is its divergence? Well, it's the partial derivative of its x component, which is 0, with respect to x, plus its y component, which is also 0 with respect to y, plus its z component, which is 1 with respect to z. And the derivative of a constant is always 0, so we get 0 for all three of them, so the divergence turns out to be 0, in line with the interpretation of it being how much going away from a certain shape. The answer is there is as much going in as coming out, so the divergence should be 0. The third example was this vector field. It is given by the expression 0 x hat plus 0 y hat plus z hat. And so its divergence is the partial derivative of its x component, which is 0 with respect to x, plus d0 dy, plus dz with respect to z. And this is 0 plus 0 plus 1, so we get 1. It is also positive, but not as large as the one of the first example. So this is how to calculate the divergence of vector fields. The third kind of derivative is the curl, and we write it as the cross product between the del operator and some vector field v. Remember that the cross product can be calculated by calculating a determinant where the first row in the determinant are the unit vectors, the second row are the components of the first vector, in this case of del, so we get ddx, ddy, and ddz for its components, and the third row are the components of the second vector, which is v in this case. Now you can work out this determinant, and what you will see is you get this expression. And what we see is it's a vector whose components are differences between partial derivatives of the vector, of the components of the vector field v. Again, the actual interpretation will come in the next lesson when we look at integrals, but it has to do with the amount of rotation there is within that vector field in some mathematical sense. So for instance, for this vector field, we will see, and we will calculate it on the next slide, that there is an amount of rotation, so in some sense there is a curl here. Now, just to point out, if I look at the curl of any of the three vector fields we considered in the examples for the divergence, you will see that they all are 0 because there is absolutely no rotation there. In the second example here, we will also see that there is a rotation, that the curl is not 0. Now, it may not look like that, but think of it in the following way. If we think of this vector field as the flow of some current of water, let's say in some river, and I put a stick in there like this, the right-hand side of the stick will be pushed upward because the current there is upward, while the left side of the stick will be pushed downward, and as a consequence the stick will start rotating. In this sense, there is some form of rotation in there, and because of that the curl will not be 0. Let us calculate it in a couple of examples. Let us look at the two examples we just considered. For the first one, the vector field can be expressed as minus y times x hat plus x times y hat. You just have to plug this into a computer and you will see that if you plot this, you would indeed get this vector field that I just drew here. What is its curl? Well, we saw that for curls we can calculate them using the determinant. So it's the determinant where the first row are the unit vectors x hat, y hat, and z hat. The second row are the partial derivatives ddx, ddy, and ddz. And the third row are the components of v, which is minus y in the x direction, x in the y direction, and 0 in the z direction. And if we calculate this, we get x hat is multiplied by the derivative of 0 with respect to y minus the derivative of x with respect to z. Both of these are 0, so the component in the x direction is just 0. Plus, in the y direction, we would get y hat multiplied by d of minus y with respect to z minus d of 0 with respect to x. Once again, both of these are 0, so also the y component vanishes. Plus, in the z direction, z hat, you get dx by dx, which is 1, minus d of minus y by dy, which is minus 1, and so we get, as a result, 2z hat. So it tells us something about the fact that the rotation is around the z-axis, and that number says something about how much rotation there is. Again, the exact expression will come in the next lesson, but for now, at least it shows us that it is related to the rotation of the field. The second vector field we considered for curls was this one. It can be expressed as x times y hat. And calculating its curl, we get x hat, y hat, z hat, d dx, d dy, d dz, and the final row is 0 in the x direction, x in the y direction, and 0 in the z direction. And working this out would give us, in the x hat direction, we get d0 dy minus dx dz, both of them are 0, plus y hat d0 dz minus d0 dx, both of these are 0, plus z hat times dx by dx minus d0 dy. And we are left with 1 time z hat, so simply z hat. So there is also a rotation around the z axis, but with a smaller magnitude in some sense. So these are the three derivatives we need. We have the gradient, the divergence, and the curl. The gradient will be written as nabla with some scalar field behind it. So what you input into a gradient is a scalar field, and what comes out is a vector field. The divergence will be written as del dotted with some vector field. So what goes into the divergence is a vector field, and what comes out is a scalar field. And finally, the curl, what comes into it is a vector field, so we can write it this way, and what comes out is again a vector field. These play a huge role, all three of them, in physics in general, and specifically in the physics of electromagnetism. And notice that in the Maxwell equations, the divergence and the curl of the electric and the magnetic fields appear, and we will see what that means in one of the later lessons. So what are the rules of differentiation? Well, first of all, for sums, we know for functions of one variable that the derivative of a sum is the sum of the derivatives, and the derivatives of a multiple of a function, so we think of lambda here as just a number, just some scalar. The derivative of a multiple of a function is the multiple of the derivative. What are the analogs of this for gradients, divergences, and curls? Well, they are exactly the same rules. The gradient of a sum is the sum of the gradients. The gradient of a multiple of a function is the multiple of the gradient. Exactly the same rule holds for divergences. The divergence of a sum is the sum of the divergences, and the divergence of a multiple of a vector field is the multiple of the divergence, and exactly the same for the curl. The curl of a sum is the sum of the curls, and the curl of a multiple of a vector field is the multiple of the curl. So with sums and with scalar multiples, there is absolutely no difference between the rules of functions of one variable as we're used to and the fields we are considering now. For the product rule, on the other hand, it is much more subtle and complicated. So this is the rule as we know it for functions of one variable. If we take two functions f and g, the derivative of their product is the derivative of f multiplied with g plus the derivative of g multiplied with f. What does that look like for gradients, divergence, and curls? Well, the thing is, first of all, how do we get those multiples? Remember, what a gradient does is it takes in a scalar field, and what comes out is a vector field. How can we plug in a multiple that gives us a scalar in the first place to put into the gradient? Well, one way to multiply two fields and get a scalar field out of it is to multiply two scalar fields. In this case, f and g are two scalar fields, and the gradient of the product of f and g is, and that is the same rule as the one we have for functions of one variable f and g, we get just g times the gradient of f plus f times the gradient of g. That is exactly the same rule that we have above, and the proof of that is exactly the same as the one we would use for that of the function of one variable. Of those differentiation rules, we will have several of them. I will just prove one of them as an example, and I leave all the other ones as an exercise for you to do. A second one is how can we also get a scalar field by multiplying two vector fields? Well, by dotting them. So if I take two vector fields, v and w, and I dot them, I get out of it a scalar field. And that scalar field can be put into a gradient. Now, it turns out that if you want to calculate it, you get this horrible expression here involving divergences and curls. It's horrible. The proof of it, I don't even recommend trying to make it because it is a very long proof. It's not difficult, it's just very tedious. It requires a lot of writing and making sure that all the components are set in place correctly. If you really want to do it, go ahead, but I warned you, it is a long proof. But one thing that I do want to emphasize, we need to know it because we will use it quite a bit. But notice that this thing here, we haven't actually defined it. What do we mean by dotting a vector with nabla, but in this order? Well, what we mean is the following. If we write v dot del applied to some vector w, if we want, for instance, the z component of that, all we mean is v dotted with nabla, applied to the z component of w. So that means it's of the form vx ddx plus vy ddy plus vz ddz wz. So similarly for the y and the x component. So those two expressions at the end of the formula here, these two, it's just a notation for what is written below it. So this is the two rules of differentiation of products for gradients. How does it look like if we look at divergences? Well, remember, for a divergence, what we plug in is a vector field and what comes out is a scalar field. So how can we get a vector field by multiplying two fields? One way is to multiply a scalar field with a vector field, f and v, and it turns out that the divergence of that is equal to the field f multiplied by the divergence of v plus v dotted with the gradient of f. Notice that both of these give us scalar fields as an output, which is what we would expect to have from a divergence. This proof is not extremely complicated. I leave it up to you to make it as an exercise. I will work out one of the other ones. Another way to get a vector field out of two vector fields is to cross them with each other. So we can take the cross product of v and w and then take the divergence of that. Now it turns out that this is equal to the dot product of w with the curl of v minus the dot product of v with the curl of w. Again, the proof is not extremely difficult, but it does take a bit of writing. Finally, for the curl, we need again to put in a vector, so we can use exactly the same two ways to get a vector field from the multiplication of two fields to get a vector field to put into a curl in this case. The first situation was to multiply a scalar field with a vector field that gives us a vector field, and putting it into a curl gives us f times the curl of v minus v crossed with the cross product of v with the gradient of f. This is the one I will prove on the next slide. And finally, the curl of the cross product is this horrible looking expression here, which uses again that same notation we introduced on the previous slide. Now again, this is not a difficult proof, but it is very long. Writing it out requires some time, and if you really want to do it, feel free to do so, but again, I warned you. So let us look at number 5 as an example. What I want to prove is this statement. I want to show that the curl of f times v is equal to f times the curl of v minus v crossed with the gradient of f. How can we prove this? Well, let's start by writing out exactly what the left-hand side means. The left-hand side is the curl of f and v, and we saw that the curl can be calculated working out this determinant. If we work it out, we get the following expression here. Now notice here that in the partial derivatives, in all 6 partial derivatives, we take the derivative of a product of two functions, of f and some component of v. So this will give us in total 12 terms when we use the product rule for functions of one variable as we know them from earlier. Using that, we get these expressions. The ones at the bottom are all the ones where f is not derived, so where f is taken out of the derivative and we derive the components of v. The top row is the one where all the f's are derived and the v's are taken out of the derivative. Now if you look at that expression, the one at the bottom with the f is f times something, and that something is exactly the curl of v. So we get f times the curl of v, so that is one of the two terms. The other one, the one at the top, is exactly what you would get as the cross product of v with the gradient of f. Notice it's a cross product of v with partial derivatives of f, but with an extra minus sign. If you just go through it line by line, you will see that it uses exactly what we defined earlier. So this is the proof of this fifth property. We looked at derivatives of functions, but what can we say about second derivatives? So remember, a gradient starts with a scalar and outputs a vector. If we want to take an additional derivative of the output, we need something that allows us to take a derivative of a vector field. We cannot take a gradient of that anymore because gradients take as an input scalar fields, but we can take the divergence or we can take the curl of that. So one possible second derivative would be take the divergence of the gradient. A second one would be take the curl of the gradient. So those are two possible second derivatives when the first derivative is a gradient. Another option, remember, divergence takes in a vector field and outputs a scalar field. If we want to take another derivative of this, the only way to take a derivative of a scalar field is by a gradient, so we get the gradient of the divergence. And for the curl takes in a vector and outputs a vector. If we want to take the derivative of that, again, you cannot take a gradient of a vector, so we're left with either the divergence of the curl or the curl of a curl. And we will go through each of them to see what they mean and how to use them. The first kind of second derivative we have is the divergence of the gradient. Now remember, the divergence is the partial derivative with respect to x of the x component of the function, which is in this case the df dx itself, because that is the x component of the gradient, plus the y derivative of the y component, which is df dy, plus the z derivative of df dz. So what we get is the sum of the second derivatives of the function with respect to each of the components separately. That is the divergence of the gradient. Now, this gets a name. It's called the Laplacian, and we write it either as the divergence of the gradient, or as that del operator squared applied to f, or as a normal triangle applied to f. This Laplacian is an operator. It takes as input a scalar function and it outputs a scalar function, and it is extremely important in physics and specifically in the physics of electromagnetism. We will study it at depth in one of the next lessons, and we will use it a lot throughout the course. A second kind of second derivative is the curl of the gradient. Now this turns out to be zero. The proof of it is not very difficult. Try to write out the x, y, and z components of this expression and you will see that they all give zero. So the curl of the gradient is not a new kind of derivative, we just simply get zero. The third kind of second derivative we have was the gradient of the divergence. Now this is not necessarily zero, but for some reason it turns out not to appear very often in physics, and because it is not important from that point of view, it has not received its own name. I will not go into it much further simply because we won't be needing it very much. The fourth possibility was the divergence of the curl. This also turns out to be zero. Again, the proof is not difficult and I leave it up to you to actually write it out, but we will use this fact also throughout our calculations in this course. And the final kind of second derivative is the curl of the curl, and it turns out to not really be a new kind of second derivative, but a combination of some of the derivatives we've already seen before. It is the gradient of the divergence minus some special kind of Laplacian. So we have a Laplacian, but look above, the Laplacian was defined as some operator that operates on scalar functions. What I write here at the bottom is a Laplacian but applied to a vector function. So what do we mean by that? We define the Laplacian applied on a vector function if I look at the x component of that thing, it's just a notation for the Laplacian of the x component. Similarly for the y and the z component, it's just a notation for that. And so these are the second derivatives we need. Now, in theory, we can go on and look at third, fourth, fifth, and higher derivatives, but it turns out that, again, for some reason, in physics, second derivatives almost always suffice. There are very few situations in which we need derivatives higher than second derivative. And so if we will need them at some point, we will discuss them in due course. But if you are comfortable with derivatives up to the second order, you should be completely fine. This is what I wanted to tell you about derivatives. In the next lesson, we will look at integrals and how to translate everything we've seen here, but on the integral side of calculus. I'll see you then.